we can kind of go through a few things today, just about exponents in general, and then look quickly at two kind of the base graphs of exponential functions, which is more graphing, which is super fun when you're trying to use this tablet there. Oh, just the top of my head. I like the screen laid down a little bit more, but maybe if I put it up on books or something, it would be easier. No. So the other day, yeah, today's Thursday, we talked about just basic exponent rules because they're going to come in handy. We're going to look just at some simple things with exponents, what writing things as powers quickly. Again, grade, technically I think this is grade 9. Number 2 is 2 to the first power. Anything to the power of 1 is whatever the base is. We can look at these in terms of factor trees. Well, that's 16 is 4 times 4. So this is 4 squared. But each 4 we can break down into 2's. So it's 2 to the power of 4. 64 is 8 squared, which is 2 times 4, and then another 2, and another 4. You can go down into, oh, not that, but 2, 2, so 1, 2, 3, 4, 6 of them. 32 actually is 2 to the 5th power, because 8 times 4, well, we just said 8 was 2 times 2 times 2, 2 and 2. 128 is 2 to the 7th. That would be 2 to the 8th, 2 to the 10th, 2 to the 11th. So we have all these powers, which we could kind of put together and do a graph. 512, it would be in between there. If you've played or seen the game, I think it was called 2048. It was all about powers of 2, trying to get things to join together. And we can have things that are more than powers of 2s. 125 is 5 times 25. This is 5 times 5. This is 5 cubed. This is 9 squared, or 3 to the 4th. 10 to the negative 3 is 1 over 10 cubed, which would be 1 over 1,000. This is kind of the basis, and we're going to look at it in a second. Where did my cursor go? Why do I not have that? There it is. Of scientific notation. Negative exponents. This is 1 over 2 to the 1, which is a half. 1 over 2 squared, which is a quarter. 1 over 2 cubed is an eighth. 1 over 2 to the 6th, which we said was 64. 1 over 64. And for someone like Hayden and those of you who enjoy computer coding, all these powers of 2 will seem a little bit familiar because binary is solely based on powers of 2. So we can do these for all sorts of other numbers. This is, whoa, how did I do that? I cut my thumb, so holding onto this pen is a little bit tricky. 6 squared. Well, something like 20, when we talked about 32, is 4 times 5. Well, this is 2 and 2, so this is 2 squared times 5. And that's the basis of our root. 625 is 25 squared. Those are both 5s. So 625 is 5 to the power of 4. Again, stuff you've done. These two are a little bit 1/5 to the 1/2. Well, the kind of quotient, power of a quotient, this is 1 to the negative 2, which is irrelevant. This is 5 to the negative 2, which, well, 1 to the negative 1/2 is that. Well, if I have a negative exponent, that's 1 over 5 squared. Well, I don't like that. 1 times the reciprocal, which is 5 squared, over 1, which is just 5 squared, or 25. So when you have these, you flip it over, change the sign. It's the same thing. I did that with grade 10s last semester, I think. Scientific notation, which you talk about in physics, a little bit in chemistry, and all of this. Well, 2.43 times 10 to the power of negative 3. That's 1 over 10 cubed. So this is 2.43. Well, 1 over 10 cubed is 1 over 1,000. 1 over 1,000 is 0.001. Multiplying that, move the decimal place 3 back to the other way. 1, 2, 3, 0.00243. 1, 2, 3. That's all place value and all of that. So that's just a quick little blurb about exponents, some more rules and the like. So graphing an exponential function is where we're going to start. We need to look at what a base function looks like, just like sine, just like the square root of x. We need our key points. Now, these ones can get a little bit tricky because, well, this is a base of 2. I could give you transformations of 7, 5 to the x, y equals an 1/8 to the x. There's all sorts of different ones. So we start with 2s because they're fairly straightforward. I'm going to draw a bit of a graph, look at the important things and what this technically is. This will be the same for a 5, a 10, a whatever. This 2 to the power of x means a doubling. So if we have x is negative 3, 2 to the negative 3, well, I'm just going to do it up here. 1 over 2 cubed, which is an 1/8. Is it easy to graph 1/8? Not really. See, we've picked up a couple more. Hello, everybody who's joined us late. 2 to the negative 2 is 1 over 2 squared, which is a quarter. Still kind of tricky to graph. 2 to the negative 1, which is a half. Well, on that grid, that's not too big of a deal. 2 to the 0 is always going to be 1. There's going to be one of our key points. Whoa. 2 to the 1 is 2. For base of 2, this is okay, but those are usually going to be our key points. Sometimes we can extend that. 2 squared is 4. 2 cubed is 8. So I'm going to start with the ones in the positive part because just a sec, Ben's talking to me. What was that, bud? Apparently he's doing Lego on the iPad. He's quiet. That's the important part. So 0 and 1. Over 1 and up 4. Over 1 and up 2. Over 2 and up 4. Over 3 and up 4, 5, 6, 7, 8. So this one, well, over 1 up 1, over 1 up 2, over 1 up 4. And that's kind of similar to a parabola. But if we look at the next one, 2 to the 4th is 16. Somewhere way up here. So it kind of looks like a parabola, but it's actually grows at a much steeper rate. When we look at -1 and a half is about there. -2 and a quarter is about there-ish. -3 and an eighth. Now, no matter what value I put in for x, are we going to keep getting smaller and smaller and smaller and smaller decimals? So this kind of trails off. We just kind of stop it there. No matter what happens at that line, and we usually draw a line here, no matter how small x gets, is it ever going to be 0? Technically, no. 2 to the power of -15. 2 to the power of -15. Well, that's still not 0. 2 to the power of -100. Well, that's 1 over 2 to the power of 100. It's a... What is going on? Oh, I think it's because I'm using... still not 0. No matter how far you go, that is never going to get to 0. So this line here is called a... It's supposed to be a t. We talked about these vertically with the tan function. Now I just need to learn how to spell. A horizontal asymptote. Because no matter what base it is, if it's 10, if it's 7, if it's 5, if it's 1.02, which we can do stuff with as well, that never is going to get to 0 on that side. So this side keeps getting bigger and bigger and bigger. 16, 32, 64, 128, 256, etc., etc. And one side gets tinier and tinier and tinier. So this one has a horizontal asymptote at y equals 0. And this is just, it's an asymptote, but it's like a sinusoidal axis. You can move it up and down based on a transformation. It has an x-intercept. Where is it going to cross the x-axis? In this case, it has none. If it transforms, we can potentially have that, but we'll deal with those when we do logarithms, unless it's something that's nice. It has a y-intercept of 0, and 1, and a domain. Can we put any x value in? Sure, it can go all the way into the negatives, it can go all the way into the positive. X is contained in the real number set, because you can do 2 to the pi. You can do 2 to the -1/2, any particular value. The range, oh, that was wretched. Y is bigger than 0. Whoops. And y can be part of the reals. Oh my lord, I'm sorry. Kate's crying. Hopefully she actually goes to sleep. So the same sort of thing that we've done with other graphs. Um, we are going to look at these particular bits. This is not greater than or equal to like a parabola, because no matter what value here, it's never going to actually hit 0. So that's something to kind of, if I ask you a domain or a range, you have to be able to tell the difference with a parabola or a radical function. It's greater than or equal to because it can be that value. But with an exponential function, it won't actually ever hit there, and we'll usually draw an asymptote in. Um, this is an example of what's called exponential growth, which we had examples the other day. Compound interest is exponential growth, assuming you don't take any money out. Bacterial viral growth. The kind of story I was always told when thinking about exponential growth is, this is going to be a very poorly attempted chessboard. Most people have seen a chessboard. I'm going to try to approximate it to 3, 4, 5, 6, 7, and the same thing. Oh, that was awful. Gotta redo that, sorry. Chessboard has 64 squares. And this was told to me by my high school math teacher, and I always talk about it when I talk about exponential growth. Chess is a war game. Fundamentally, chess is a war game. It's about combat. It's about taking and destroying and capturing other pieces. So the old story was some sheik or emir or some king in the Middle East area region wanted a game for his generals to play to get better at strategy. Well, and then that's what chess is. It's a strategy game. Um, so he went and got a mathematician to design a game, and the mathematician came back and said he designed chess, and the king was all happy, and this is awesome and great. And the king said, well, how much do you want to be paid for it? And the mathematician said, I don't need gold, I don't need money. Give me 1 grain of rice for the first square, 2, and then double it every time. 2, 4, 8 grains of rice. Well, geez, that doesn't seem 16, da 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 da. Well, that's 2 to the 0. So if we snake up here, the last one would be 2 to the power of 63. That's a lot of grains of rice, no matter how you count it. Well, the square before that is 2 to the 62, 2 to the 61. There is a way with sums and calculus to figure out how many that would actually be. Um, and then the kind of punchline of the story is the king figured out, wow, that's a lot of rice. We don't have enough of that. So he just had the mathematician killed because, well, he had the game. Why would he pay him? And, well, it was vicious, but that's how exponential growth can grow really quick. If you got $1 a day versus $1,000,000, depending on how long those, and the dollar doubles, 1, 2, 4, it's actually better to take the other one. So that's exponential growth. That's super awesome. We're going to look at things where b is in between 0 and 1. So this is a nice simple one. And we can look at this, a half to the x. Well, I can put 1 to the x over 2 to the x. Well, that's just 1, so that's irrelevant. 1 over 2 to the x, which is the same as 2 to the negative x. If we have a negative in front of the x, we are, based on transformations, reflecting this in the y-axis. So a half to the negative 3 is 1 over the reciprocal of a half to the third, which is 2 cubed, which is 8. And if you don't trust me, you can throw it in a calculator. To the negative 2, which is 4. A half to the negative 1 is 2. Anything to the power of 0 is 1. A half to the power of 1 is a half. A half squared is a quarter. A half cubed is an eighth. 8, 4, 1 minute up. Interesting. It's all of the values are flipped. Negative 3, 1, 2, 3, 4, 5, 6, 7, 8. Negative 2 and 4, negative 1 and 2, 0, 1, and then we kind of peter off. A half, a quarter, an eighth. Pardon my horrific drawing. So as we go further into the negatives, well, we've taken everything and flipped it. I can draw a horizontal asymptote again. We usually abbreviate that because we don't want to write that as horizontal asymptote over and over and over again of it's still at y equals 0. So the horizontal asymptote is y equals 0. The x-intercept, the point where y equals 0, well, there is none. The y-intercept is still 0 and 1. The domain is the same because we've just reflected it. The range is also y is greater than 0. Y is contained in the reals. So same thing, same idea, nothing different. This, is what we call exponential decay because it's going down and down and down. I think that one had probably the best example that I always think about radioactive decay. You will hear, or you may have heard, the term half-life, and we're not talking about the video game. Half-life is a duration of time in which half of a particular radioactive sample decays into something else. So one that's kind of common, carbon-14 for carbon-14 dating, I think is about 5,500 years. And that's how scientists date organic material because it has to have carbon. They know what the ratio of carbon is and they extrapolate back given that half-life. If you're looking at the heavier elements way down at the bottom of the periodic table, some of them have half-lives in the billions of years. Some of them have half-lives in the fractions of seconds. So there's ways to model those. It's actually a graph similar to this, but we have a transformation in there. So those are our basic things. This is just one of Mrs. Legier's things. Well, if you have 7 to the x, well, this is 7 to the x. This one is 7 to the negative x, or 1 over 7 to the x. Growth and decay, very similar. We can reflect things. So I don't know why. Tomorrow we'll look at just the quick shape of those, transformations, um, and potentially some graphs, but really just reading transformations and go from there. So that's kind of my spiel for today. I don't know how many people we still have. Did I lose anybody? Maybe. All of you people who are wonderful and get up nice and early. So if there is no questions, that's all I was hoping to get through today. Hopefully it didn't go too quickly.
Mr. McKay,
Yes.
is the assignment on files now?
Assignments are under the assignment thingamadoohicker.
Oh, okay. So it's on there though.
I don't recall. Maybe I didn't put it up. Oh, apparently I did not. I will do that. I'm not going to sit and do it while you guys are here because that's a waste of your time. But I will. Is it? Was I stupid enough to put it under files? I don't think so. If it is, I'm sorry. Yeah, I'll put that up today. I'm sorry, I totally forgot about that. Anything else? If not, you guys are free to go and enjoy another rainy day. You're welcome. Have a good day. You're welcome.